Okay, so first of all, thanks to the organizers for inviting me to speak here. So I apologize if some of you have seen parts of this talk before. So this is mainly kind of covering the work I did during the Gung Ho project with the Met Office. And I'm going to talk about solvers and preconditioners for atmospheric fluid dynamics. I will actually not talk about next generation time-stepping methods. I will talk about quite an old time-stepping method, which is kind of semi-implicit time-stepping, but it's still a very important one. So I'm going to talk about solving large systems, preconditioning large systems when you kind of do that. And I think Lawrence is then later going to talk about how to write efficient software, how to use efficient software to do this. So this is obviously work done together with lots of others that I haven't mentioned here in Bath, at the Met Office, here at Imperial, in Exeter, lots of different places. Okay, so here's just an overview. The first thing I want to do is I just want to kind of motivate this and just introduce semi-implicit time-stepping. So for most of you, this is probably nothing new. I just illustrated for a simple model problem. Say a few words about computational challenges, but again, I think Lawrence will kind of talk more about how you can kind of overcome them when you write code, and then talk about solvers and preconditioners. And what I was going to do here is kind of try to classify this in terms of the system you're solving, in terms of the grid that you're using, in terms of the discretization, and also the order of your discretization that you're using. And it turns out that depending on where you are in the space, you kind of want to use different methods, different solvers, and so on. So I'm mainly going to focus on this Schur complement reduction to an elliptic problem and solving this. So this is a kind of a standard technique. I mean, there are others, but that's what lots of people use, and what the Met Office, for example, uses. I will talk, of course, about multi-grid preconditioners, and then in the end, I want to kind of finish up and look at kind of more modern discretizations like these mimetic finite elements or discontinuous Galerkin methods. Okay, so just to kind of start, to give you an idea what this is kind of all about, I start with a very simple model problem. So these are just the linearized shallow water equations. So I have linearized these around a state of constant kind of advection. So that's this advection vector here. So that's just a constant. And then my variables are the velocity u here and the height perturbation eta. And then the evolution of the u and the eta is given by this kind of coupled system here. What you see, there's kind of obviously time derivatives here, and then there's kind of two contributions. So there is this red part here, and this is kind of responsible for gravity waves. So when you kind of push water together, it will kind of try to flow out again, and it will also try to preserve its momentum. So that's kind of described by these terms here, and then these first two terms here and these equations, they just describe the advection of the system. And then you can basically write down the dispersion relation for this. So if you have a wave vector k, then the omega, the frequency, is given by this expression. So you have the advective velocity times k, and then you have the square root of g times h times the modulus of k here. And the important observation is that in most systems that you have kind of a big scale separation. So the advective velocity is typically much, much smaller than this square root of g times h here, which is the speed of the gravity waves. So there's usually a factor of 10 between these. And if you have this, one of the efficient time discretizations for this is this semi-implicit time discretization, where you basically discretize the advection with an explicit time-stepping scheme, but treat the gravity waves with an implicit scheme, and that is kind of efficient because you are not limited by the CFL condition of the gravity waves here. So this is just a model system, but the same phenomenon occurs in lots of other systems, like in the real atmosphere, for example. Okay, so let's look at this in a bit more detail. So when we write down the CFL number of the advective part, then this is just this dimensionless number here. So that's the advective velocity times the time steps twice divided by delta x. And because we use an explicit scheme for the advection, we have to make sure this is smaller than about 1. And that just basically means that in one time step, a wave kind of can't propagate over more than one grid cell. Otherwise, the scheme becomes unstable. So for the gravity waves, we can also write down a CFL number, and then that's kind of the same expression, just with the gravity wave speed replaced by the advective, with the advective speed replaced by the gravity wave speed. And so you get this number here, and this, because we have an implicit scheme for this part, this can be larger than 1. This doesn't matter, so the method is kind of still stable. So typically the scale separation is around kind of 10, so the gravity wave speed is maybe around 10 times larger than the advective wave speed. So the ratio between these numbers is about 10. So, okay, so we don't have to worry about stability for the gravity waves, but one thing we might have to worry about is kind of accuracy. So the first, sort of the advective modes, they're represented accurately because of this condition here, so let's make sure there isn't any big errors there, but you screw up the implicit modes. But that's actually not a big problem, because when you look at this from the kind of advective timescale, these waves are kind of almost instantaneous. They're kind of there for adjusting to the kind of mean flow, so representing them exactly isn't so important. They also usually don't contribute much to the energy balance, at least in the real atmosphere, that's the case. So it doesn't matter if you slow them down or accelerate them, because they're kind of almost instantaneous anyway from the advective timescale. You just have to make sure they don't, for example, propagate in the wrong direction or things like that. I mean, that would be obviously a problem. So the advantage of the scheme is that you're kind of not really restricted by this gravity wave CFL number here, so you can use an around 10 times larger time step than a purely explicit scheme. The disadvantage is that you have to solve a linear system in every time step, and I will explain that on the next few slides where this comes from, and then I will spend the rest of the talk just talking about how you solve this problem. Okay, so then hopefully tomorrow we will hear about other methods for kind of doing the time stepping in this case. Okay, so let's have a look at the time discretization then. So what you basically do is in the simplest scheme, I mean there's obviously others like higher order schemes, but in the simplest time discretization scheme you just replace the time derivative on these sides of the shallow water equations by this kind of finite difference. So you take the field at the next time step, subtract the field at the current time step, and divide it by delta t. So that's not very surprising. But then for the other terms, you kind of have to be a bit careful. So that kind of, I mean, what you do to them depends on whether you treat them explicitly or implicitly. And one way of doing this is kind of by just evaluating the advective term here. Just at the current time step, so that's just the advection velocity times the gradient times the field at the current time step. So that's just an explicit discretization. And then for the other term, for the gravity kind of gravity wave term, you take the field both at the next time step and at the current time step. You take the gradient, you average it, and then that's what you use in your equation. Okay, so and you do this in the velocity equation and also in the equation for the height perturbation. So when you do this, there's kind of a problem here, because when you look at this, you kind of have the fields at the next time step appearing kind of in two places in these equations. They appear in the time derivative, but then they also appear in the implicit gravity wave term. So that means you can't easily solve for them, and you end up with this system which is written down kind of at the bottom. So you have this kind of 2 by 2 kind of block structure. So you have kind of ones on the diagonal. So that's kind of, that's what you just get from this term in the time derivative. And then you have these terms on the off diagonal, which are basically derivatives. And if you non-dimensionalize the spatial derivative, the gradient or the divergence, then the number that appears in front of these is just the gravitational CFL number. Okay, so that's the problem you have to solve. So you have a bunch of fields on the right-hand side. So they are just determined by the kind of current state of the system. So that's just absorbed in these R vectors here. And then you solve this for the velocity and the height perturbation at the next time step. And that's kind of, that's kind of the hard bit. So you have to do that in every time step. So one thing I should say is that when you look at the system more closely, obviously when you discretize it in space, the divergence operators turn into kind of some finite difference or like finite element, weak derivatives or whatever, but they are kind of sparse. And yeah, the whole system you end up with is basically a very big, sparse linear system with this kind of 2x2 block structure. And the important thing is you have to solve this in every time step. So this is going to be expensive because it will be very, very large if you have a high discretization. And the other thing to kind of bear in mind when you look at this system is not symmetric positive. It's also not elliptic. So it's if you just were to take this system and you just try to solve this, this is probably not the best thing you kind of want to do. So you want to think about a good iterative solver maybe, and maybe think about a good preconditioner for this. Okay, so so that was just for a simple model problem. That was just for the kind of shallow water equations, which are obviously very important. So what happens if you go to the full atmosphere or to some other kind of problem, to the Navier-Stokes equations in general? So there's a few additional complications. So you have to solve this for a full nonlinear model, so this becomes a bit more complicated. But in the end, it boils down to the same. You just have to do you just have to do a Newton iteration to solve the nonlinear system, and then you have to do a linear solve in each step of the Newton iteration. The nonlinearities are usually weak, so you only need to do a very small number of Newton iterations, just like 3 or 4 or something like that. So if you have the full atmosphere, if you have the fully compressible Navier-Stokes equations, the fast waves are usually not gravity waves. The fastest waves are vertical sound waves. And the fact that they are kind of the annoying ones in the atmosphere is simply because you usually use a discretization which has very thin cells in the vertical direction and very big kind of grid spacings in the horizontal. Okay, so if you do this in a real model, like the Metofis model or whatever, and you just work out how many unknowns you end up with when you discretize this, you basically quickly realize that's quite a lot. So if you want to solve the equations of atmospheric fluid dynamics in the whole atmosphere, and you use a horizontal grid spacing of around 1 kilometer, and you use maybe 100 vertical levels, which is kind of ballpark realistic, then you end up with 10 billion kind of unknowns. So that's a lot. And then the other thing you need to do is when you do a weather forecast, you need to do this quickly, and you need to do around 10 to the 4 linear solves in about 1 hour, because you need to get the forecast out really quickly. So that means you basically have less than 1 second to solve one of these systems with 10 billion unknowns. And that's actually very challenging. So developing good solvers is important if you want to do this. No, this is the global system. So for a limited area model, you obviously have less, but then you probably want to use a higher resolution.
Just a quick couple of remarks. I mean, it's Picard iteration rather than Newton iteration. It's the same thing on the left-hand side. And it's not really treated for iterations and number of conversions. It's just that if you do that number, then you at least get a stable time step. Right? Yeah. It's nowhere near.
Sure. Yeah. No. I mean, usually you solve. There's lots of other errors in the system, and you solve the linear system to quite a loose tolerance.
Yeah. And everything's loose.
Yeah. So you don't iterate until like you get to machine precision or something like that. Yeah. Okay, so then there's a couple of additional challenges if you kind of want to really do this on a kind of modern computer. So machines nowadays have lots of cores. So I think this Taihu Light machine, which is the fastest machine on the planet, has about 10 million cores. And there's also lots of cores per node. So when you kind of code this up, you have to bear this in mind. You also have to think about, when you want to use these machines, you have to think about vectorization. So I mean, all these machines have now kind of quite wide vector units. So you really need to kind of exploit them, otherwise your code is kind of a factor 4 or 5 times slower than it could be. And that's a challenge for the implementation. So then another consideration is kind of memory bandwidth. So that's one thing you have to bear in mind when you write the solver. So the memory bandwidth on a modern chip is usually kind of much lower than kind of the computational throughput. So on a Haswell node, you can do around 6 fused multiply add operations in the time it takes to load one number from memory. Okay, and that number is, I mean, it depends on the chip, obviously, but that's kind of the ballpark. So if you have a code that's kind of memory bound, that does kind of one computation on every piece of data it reads from memory, then that code will not run at the full speed. It will just be throttled by the memory bandwidth. So then you have to worry about the memory hierarchy. So you have to think about how to move this memory around. That's obviously even more complicated if you have a GPU or something. And that's another thing that's kind of mentioned here. So you also don't just have one architecture, you have CPUs, GPUs, Xeon PHYs, ARMs, or whatever. So when you write code, you want to kind of write one code and be able to run it on all these machines and not write code for each of these. And that's just clearly unfeasible. And again, that's something that I think Lawrence will come back to later. Okay, so but these memory bandwidth considerations are, so that's something which I think is quite important when you design your discretization and when you think about that, how you can implement this in the fastest way. Because there's some discretizations which are naturally bandwidth bound and there's others which are naturally kind of flop bound. Okay, so how do we solve this system then? So one thing you could obviously do is you could just take a direct solver, Gaussian elimination, and you could throw it at the system. So that should work in principle, but it's clearly unfeasible if you have a system with 10 to the 10 unknowns. It's also not so clear how to do this in parallel. And the other thing is you don't really need to know the solution exactly. You only need to know it up to a tolerance of 10 to the minus 4 or something like that. So what else can you do? People are using spectral methods. So I hope that everything here, so this cost estimate is correct because Niels is sitting in the audience. But if you use these spectral methods, you can kind of play some tricks. So basically what you do is you kind of discretize your grid on a sphere using spherical harmonics, and then you transform your equation into spherical space where you can solve it quite easily, and then you kind of transform it back. And when you do this, you can play some tricks to make these transformations faster. And that's kind of the cost I got from one of Neil's papers. And this works quite well, so that's very competitive on current machines. You have to be a bit careful because when you do this, you end up with all-to-all communications, and that will eventually kind of kill your scalability, and ECMWF is kind of working on looking at alternatives for these spectral methods. So they're also looking at other ways of doing this. There's other limitations. So one thing is that you have to use a structured grid. So this only works on kind of logically rectangular domains. You have to approximate kind of your equation somewhere with constant reference profiles in your preconditioner and things like that. So, but that's a good method that currently works, but there are issues for exascale machines. So what else do we have? Well, there's iterative solvers, so that's what I'm going to talk about today. So there's lots of them, so they're all kind of known as these kind of Krylov subspace methods. So there's conjugate gradient, which works for symmetric positive definite systems. There's GMRES, which works for more or less any system, so it's much more robust. And there's other variants, but the basic idea is always that you kind of iteratively construct a solution to your system, and you kind of stop when you have reached kind of a certain tolerance. So the expensive bit in this is usually kind of applying the system matrix. So you have to do that very often to build up your Krylov subspace. And then you have to, I mean, there's another thing that people are often worried about, and that's kind of the cost of a global reduction, because you have to calculate dot products. So the cost for the global reduction is, you have to do order 1 per iteration, so this kind of scales with the number of iterations. And then there's a factor that goes like log p, where p is the number of processors. So people worry about this because they say, like, if p grows, then this will kind of dominate everything. But I think it's actually not really such a big problem for two reasons. So one reason is that most hardware has really good kind of support for MPI or reduce nowadays. So it isn't a problem. And the other thing is that if you have a good preconditioner, then the number of iterations is actually quite small, so you don't really have to do that very often. If you have a bad preconditioner, obviously you have to, this cost becomes more kind of important. Should also mention there's some methods that kind of avoid these kind of global reductions or reduce the number, but they usually require you to know kind of some spectral bounds, which is kind of like another kind of issue. Okay, so the other thing that's really important in these iterative solvers is to kind of have a good preconditioner. So what the preconditioner basically does, it takes your system, matrix A, and it multiplies it by another matrix to construct a matrix which is kind of well conditioned, which has kind of a small condition number, which means that the number of iterations to solve this preconditioned system is kind of much, much smaller. So one preconditioner that's kind of very, very popular nowadays is this kind of multigrid method. And that's kind of, you can show that this is kind of algorithmically optimal. So the number of, so the cost of one multigrid iteration of one preconditioner application is proportional to the number of unknowns. That's kind of the best you can kind of achieve. And there's different variants. So there's geometric multigrid, where you have to work a bit harder to implement this. And then there's things like algebraic multigrid, which you just pick off the shelf. And that's kind of a black box solver, and that you can just use them. But just to repeat this again, the two steps that are very kind of expensive in your solve is the sparse matrix vector multiply to apply the system matrix, and then the application of the preconditioner. So the other thing I should say about these iterative solvers, that might be obvious, but they can cope with arbitrary discretizations and grids, so they're kind of a bit less restricted than spectral methods. Okay, so there's lots of them out there. Which one do you kind of want to use? Which discretization do you want to use? Which grid do you want to use? Which order do you want to use? And that's kind of, that's not so obvious. And I'm just trying, what I'm trying to do here is just kind of try to classify this and look at kind of three different cases. So the first choice you have to make is you have to kind of choose a grid. In some cases, it's kind of obvious what you want to do. So if you have a rectangular domain, you probably want to use a structured grid. In other cases, if you have a more, this is a circle, so that's still kind of relatively easy. But if you want to model want to model waves in an estuary or something like that, you're kind of a bit more restricted, so you have to use a kind of an unstructured grid. So that's kind of one choice. So once you've done this, you kind of have to choose your discretization, and there's again different ones. It's very simple ones. There's finite volume, finite difference discretizations, where you basically just evaluate the solution at some points, and then you evaluate derivatives by just taking finite differences. There's finite element discretizations, where you approximate kind of your solution in a function space, which is spanned by these local finite elements. And then there's kind of more modern finite elements. So there's these mimetic finite elements, and there's kind of discontinuous Galerkin methods, which I will come back to at the very end. So that's a choice you have to make. And then in the end, you also have to choose kind of what order of the discretization you want to use. And again, there's different choices. So you could use a very low order discretization, or you might want to go to higher order, or even to spectral grids. Obviously, you have to be a bit careful. So these high order discretizations only really help if you have enough smoothness in your solution. So if you have big jumps in your solution, then a higher order method is probably not a good idea. It will not really kind of reduce the error. Okay, so I just try to, this is just a diagram kind of classifying this. So you start off with your PDE, you make a choice of your grid, and then you choose your discretization. So if you have a structured grid, you typically use finite difference or finite volumes. You can use finite elements. If you have an unstructured grid, you're a bit more restricted. You can't, you can, in special cases, you can use these kind of finite difference, finite volume discretizations, but usually you use finite elements, or, and then there's different flavors, so you might want to use these mimetic finite elements or DG or whatever. And then the last thing, you kind of worry about the order. And these finite element methods, they're kind of naturally extendable to higher orders. So you can go to, with DG, you can go to arbitrary high order very easily. And these finite difference methods usually only work for low orders. Okay, so there's kind of two kind of cases I want to go through. So there's low order finite volume methods on structured grids. So that's kind of the standard setup. That's what the current unified model at the Met Office uses, for example. It has some issues. One issue is that you have this convergence of grid lines at the pole. Then I want to talk about these kind of low-ish mimetic finite elements on unstructured grids. So that's what the next generation Met Office model will use. And this is also obviously implemented in FireDrake. And then the last one I want to talk about is higher order DG on tensor product elements. And I think they are very kind of promising because they have a very high data locality and they have very high arithmetic intensity. So they have the potential to use modern architectures really, really well. But there's still some open questions there, I think. Okay, so let's look at the first case. So the first case is finite volume on structured grids. So that's this branch here. So you can only do kind of low order in this case. And what do you do in this case? Well, you start with a system here. So this is the system we want to solve. I just moved the system matrix to the other side. So basically the fields at the next time step are given by the inverse of the system matrix here applied to the right hand side. And then I do kind of the standard trick. And that's basically just taking this matrix here, taking the system matrix here and writing it as a Schur complement. So you can show that this matrix here, the inverse of this matrix here, can be written as the product of kind of true triangular matrices here, and I mean they're really block triangular. Then you have a diagonal matrix, a block diagonal matrix in the center, and there's a 1 in the upper part here, and then there's this h to the minus 1 in the lower right corner here. Okay, so that's kind of the hard bit. So when you apply these three matrices, the first thing you do is you apply this kind of lower triangular matrix, but that's very easy. You just take, nothing changes in the first component. In the second component, you just take the derivative of the right-hand side for the velocity, apply the gradient, and then you add the right-hand side for the height perturbation, and that gives you a new kind of right-hand side. And then you have to apply this middle thing here, and here you actually have to do a solve. You have to solve for this matrix H here, and this matrix H here is this operator H here is this Helmholtz operator, so that's nothing but kind of the identity operator, and then I subtract a Laplace operator, and this Laplace operator gets k'd with the square of the CFL number here. So that's quite important that you have this in here. And recall that nu is around 10 in most applications, so it's not huge. Okay, so that's, and then once you've done this solve, you kind of need to take this and you need to apply this upper triangular matrix, but again, that's very easy because you just have to apply this divergence operator and combine the fields. So that's kind of the standard strategy. I just briefly want to mention this other method here, which is very similar, obviously. But if you have an incompressible fluid, you can use this projection method. And what you do there, so this is just written down for these incompressible Boussinesq equations for simplicity. So what you do there, so you have basically a fluid which is incompressible, so the divergence of u is 0. So that was not the case for the fluid we looked at before. But what you can do in this case, you basically, so these are just the Boussinesq equations here. So you have an equation for the velocity evolution. Then you have an equation for the buoyancy here. And what you do here is you do the following. So what you do first is you basically, you take this term here and you take this term here. You take the right-hand side of the velocity equation. And you integrate this to get what's called a tentative velocity. So you integrate this term here, and you get this u tilde. But this u tilde isn't divergence free. So if you just do this, you end up with a U tilde which has a non-vanishing divergence. So that's obviously not what you want. So what you do then is you basically just add another correction to this, and that's a gradient of a pressure term, and this pressure term here is constructed so that the divergence of the field at the new time step, the velocity at the new time step, is actually 0. Okay, so that's basically written down at the bottom. And if I just enforce this condition, I just apply the divergence to this equation, you end up with 0 on the left-hand side, then the divergence of U tilde, and then you have kind of the Laplace operator acting on this new pressure here. Okay, so that's the idea. And then, so that's written down again here. So and then you just have to solve this equation for the pressure here. So basically solve this Poisson equation for the pressure. So you have Laplace applied to pressure is the inverse time step times the divergence of the tentative velocity. And when you solve this equation, you recover the pressure, and then you can add this to correction to the tentative velocity to get the correct velocity. So this is all quite nice. So one thing to bear in mind is that here you have to solve a Poisson equation. That's a bit different. And you also have to be a bit careful, and that's kind of the downside of the method with boundary conditions. So if you just have these very simple boundary conditions, if the divergence of U, if the normal component of the U is 0, then you can basically show that you get a very simple boundary condition for the pressure correction. But if that's not the case, you basically have the field, the normal component of the field at the next time step appearing in your equation. So you have kind of this coupling between the velocity at the next time step and the pressure. And that's a much harder equation to solve. So you can't just solve this equation here. Okay, so that was just kind of a quick aside. But let's come back to solving these equations. So as I said, for the incompressible fluid, you have just the Laplace operator. So the operator you have to solve for is just this here. So this is symmetric positive definite, so you can just use a conjugate gradient method, like bicycle step or whatever if it's not symmetric. But in this case, you just use conjugate gradient. The problem in this case is that the condition number actually diverges. If you have a finite grid, the condition number grows, so solving this equation becomes more and more expensive. Okay? But that's just for the incompressible flow. If we go back to the compressible flow, which I started off with, it's a bit different. So in this case, we have this Helmholtz operator. So in addition to this Laplace operator, we have another kind of zero-order term. And that makes things much easier. So the operator you have to solve for is basically 1 minus, and then the CFL number squared divided by 4 times the Laplace operator. And you can then work out the condition number of this, which is obviously very important for your SIG iteration. And this is approximately 1 plus 2 pi squared times nu squared. And this is around 2000. And the important thing is that this doesn't depend on the resolution. And the reason this doesn't depend on the resolution is because you always want to adjust the time step size such that the nu is kind of constant and around 10. Okay. So and then you can work out the number of iterations for the CG method, and up to kind of a constant here you basically get the CFL number times the log of the tolerance that you want to solve it to. You typically want to solve to maybe 10 to the minus 4, and if you do the math, you basically discover that you have to do around 200 iterations to solve it. Now, that already sounds quite a lot. I mean, if you have to do 200 iterations, that's not really a method that converges really fast. So the question is, can you do better? And you can do better by using a preconditioner. And you can actually reduce this to around 10 if you use multigrid. And that's what I want to show now. So multigrid basically works as follows. So basically what you do is you start off with your solution on the kind of finest grid. And you construct a series of coarser grids. And you use these coarse grids to kind of accelerate the solution on the fine grid. So how do we do this? So what you do is you apply a very simple smoother on the finest grid to remove any high frequency error components. So that's like a Jacobi iteration or SOR or whatever. Then you calculate the residual, you move this to the next coarser grid, and you solve the coarse grid equations on this coarse grid. And that's obviously much cheaper, simply because you have less unknowns on the coarse grid. And then you kind of go back and correct the solution on the fine grid. So you can iterate this, so you can kind of go from the fine grid to the next coarsest grid, and then you go all the way down to a very coarse grid where you maybe only have kind of 10 unknowns, and you can solve this directly, and then you go kind of back. And these coarse grids, they don't really add much to the cost. They kind of just accelerate because the solution is kind of the number of unknowns is smaller and smaller on the kind of coarser grids. And you can then actually show that, I mean, you remove the errors on all length scales because kind of the error on every grid has like a, well, on each grid you kind of kill one length scale in your error. And if you do this, you can basically reduce the error, I mean, not just in the fastest modes, but basically all the errors in the solution. Okay, so, and you can also show that this is algorithmically optimal if you do it properly. Yes?
So V-cycles aren't quite, because you need like long error V-cycles to reduce.
Yes, that's correct. So if you just do a V, so Lawrence just said that this is not correct for a V-cycle. So if you just do a V-cycle, you will not get this optimal convergence. Strictly speaking, what you need to do is you need to do a full multi-grid cycle where you start on the coarsest grid and then you kind of go down and then you do V-cycles of increasing size. But if you do this if you use this as a preconditioner, one V-cycle is kind of sufficient. Yeah. Okay, so that's kind of the algorithm, and there's a really nice, this algorithm has a really nice property if you solve the compressible equations, and that's the following. So if you look at the Helmholtz operator again, so this is written down here, then you can write down the kind of Green's functions for this operator on an unbounded domain. And they basically look like this. So you have this kind of 1 over x minus x0 decay here. And then you have this exponential term here. And this exponential term is suppressed by a typical length scale, which is given by half the current number. Okay, so that comes from the fact that I have something in front of, that I have the zero order term here. If this wasn't there, this wouldn't be true. But with this term here, I have this kind of nice exponential suppression. And that basically means that you don't have any kind of coupling over more than around 10 fine lattice sides. Okay, so the lambda here is basically half the CFL number, so this is around kind of 10, at the order of 10. So and that means that when you do the multigrid iteration, the operator becomes increasingly well conditioned on the coarser levels. So on the coarser levels, the operator becomes more and more well behaved because the CFL number kind of decreases on the coarser levels. Yeah, this nu here depends on the grid spacing. And that means that you can get away with only using a very small number of multigrid levels. So you don't have to go down all the way to the bottom. You can just do 3 or something like that levels. And that is kind of sufficient. And that has nice kind of advantages if you solve in parallel. So that's not true if you do incompressible flow. If you have incompressible flow, you have these instantaneous sound waves. They have kind of an infinite speed, so they kind of causally connect all parts of the domain with all other parts. And there you have to go down all the way to the coarsest level in the multigrid. Okay, so this is just kind of a numerical experiment here. So what we did here is we basically looked at the number of iterations and the total solution time for different CFL numbers. And we used kind of 2 different methods. We just used a simple CG iteration, so that's the red lines here. And then we used kind of a multigrid method with different numbers of levels. And what you see here, if you use just CG, the number of iterations is around 100. This is kind of in the ballpark of what you would expect. And if you do multigrid, this really brings it down to around 10. And you also see that doing additional multigrid levels doesn't really help. So at a CFL number of 10, whether you do 5, 7, or 10 multigrid levels doesn't really make any difference at all. It doesn't change the number of iterations, but it also doesn't really change the time, which is also not surprising because these are so cheap that they don't cost anything. But this might be important if you do this in parallel, because it's much harder to parallelize on the coarser levels. So what you see then, if you increase the CFL number, eventually there is kind of a difference where the kind of 5-level multigrid becomes inefficient, but you have to go really, really far until this kind of kills you. Okay, so yeah, that's just coming back to this. So one nice thing about this reduced number of levels is that you get improved scalability, because if you have to coarsen all the way to the coarsest grid, you eventually end up in a situation where you have kind of less grid cells than you have processors on your massively parallel machine, and that's obviously a problem. So you have to start pulling data together. So that's what we did in this paper here. But I mean, it also doesn't really make a difference. In these problems, you can get away with a small number of levels. So the other thing that's kind of helping here is that if you only have a very small number of levels, then probably what you want to do is you want to kind of assign one coarse grid cell to kind of one processor, kind of one compute node, and then you kind of want to use kind of shared memory parallelism on a node and kind of give one thread to each fine grid cell, and then as you kind of coarsen, you kind of don't have to exchange data, you just kind of let some of these threads go idle. So that's kind of a natural way of doing it. Okay, so that was all kind of only for two-dimensional problems. So what happens if you go into 3 dimensions? And there's a few things that are a bit kind of particular about the atmosphere. And one thing is that it's very thin. So you have this very thin kind of spherical shell. And you can also write this as a kind of tensor product grid. So you have a grid which is in principle unstructured in the horizontal, and then at each horizontal grid cell you attach this whole column of data. Okay, and you can show, and I don't want to go into all the details, but what you can basically show is that you can take your multigrid solver, and if you adapt it correctly, you can basically end up with something which behaves like a 2D multigrid, and which doesn't care about these kind of vertical sound waves that kind of might kill your performance if you don't do it carefully. Okay, so that's this kind of tensor product multigrid idea. So basically what you do, if you have a shallow domain, the vertical grid spacing is much smaller than the horizontal grid spacing. So you have this very strong anisotropy. If you write down your matrix for your problem and you organize the data so that columns are contiguous, what you basically see is that you have very strong coupling in each of these vertical columns. Then you have weak coupling between the columns. And you can kind of, you can basically then deal with this by just using a very particular smoother in your multigrid, which just kind of inverts these columns, these blocks which depend only on data in one column, and that's a strictly local operation. So that's kind of very easy and doesn't really add much overhead. So that's kind of the idea between this tensor product multigrid. So you only coarsen in the horizontal direction, and then you do vertical line relaxation, and then you can show that your convergence is just set by the horizontal CFL number, and you don't get killed by this kind of vertical CFL number, which becomes very large due to this fine grid spacing. Okay, so what about algebraic multigrid? So one thing you could do is instead of doing this geometric multigrid that I explained, where you kind of move between these grid levels, you could just use this kind of black box solver, which was basically developed for more general problems. So the idea there is that you basically can apply this to any matrix. It doesn't have to come from a discretization, and it just works out the kind of the structure. It just works out these coarse levels purely algebraically. And there's different implementations. There's this Boomer AMG in Hyper. There's one in this Dune library, and there's probably lots of others. But basically, the nice thing about these is you just give it the assembled matrix, and then it just does everything itself. It will adapt to any anisotropies. It will also adapt to kind of local anisotropies and things like that. So it's very nice. So it works basically for almost all cases. But it has a few drawbacks. So one drawback is that you have additional assembly costs because you need to construct these coarse grid matrices. So this can be quite expensive. You also have to assemble the matrix. So if you use geometric multigrid, you might not do this. So the other thing is that it has lots of parameters that need tuning if you want to achieve optimal performance. And then the other thing is that for some discretizations you have to be a bit careful, because the stencil size, if you use a very simple finite volume or finite difference discretization, the number of elements in your stencil kind of grows. So on the finest grid you only couple to your nearest neighbor, so in 2D you just have 5 entries in your matrix, but then in the coarser levels you kind of create additional couplings, these kind of diagonal couplings here, and that obviously makes the method less efficient, because you don't have such a big saving from going to coarser levels. So that's kind of AMG, but it's like, because it is kind of so easy to use, it's often the first thing you might want to try. So one other thing that is kind of quite important when you kind of implement these methods is whether you use a matrix-free or matrix-based implementation. And that's still like this very simple discretization. And what we did here is we kind of used both a matrix-free and a matrix-based implementation. And when you purely look at the number of floating point operations and memory references that you need to apply the matrix, okay, then you kind of you can write them down, and you basically see that for each matrix row you have to do kind of around 14 flops, well, in both cases, so that's always the same. But the memory references for the matrix-based cases the number of memory references is much larger, because in addition to your vectors you have to also read the matrix from memory. So you have to read the entire matrix stencil, which in 3D would be 7 elements. And then if you divide these two numbers, you get an arithmetic intensity. And for the matrix-based method, you basically do 1.6 flops per double that you read from memory. So that's kind of very, very bad. Okay, so you're clearly memory bound. If you use a matrix-free implementation, it's kind of much better. And that's kind of illustrated by these numbers here. So that's just total solve times for different solvers with so that's weak scaling, so the number of compute cores increases. And if you just compare the two the two multigrid methods, so that's the red line here, that's a geometric multigrid, which is matrix-free. And then there's these two blue lines here, and they are both algebraic multigrid methods. And what you see here, there's kind of almost a factor 10 difference. Okay? And one of the reasons is really the fact that you use a matrix-free implementation, so you don't have to load the matrix from memory. Okay, and that's quite significant, and that's very important on modern architectures. So the bottom line from this is really, if you have a very simple discretization and you don't have to store your matrix, obviously that only works if the matrix is very simple, then you probably want to use kind of matrix-free to do this. So it's about 10 times faster. I mean, this was on Hector, so I don't know how this looks on other machines. On GPUs, it's probably a very similar picture. Okay, so that was kind of a very simple, kind of low-order finite difference, finite volume discretization on a structured grid. So what I want to do now is before I move to the next one, I wanted to just briefly show some results from a real code. So this is the endgame dynamical core used by the Met Office. So what we did there is we implemented a multigrid solver as an alternative to the current BiCG step method. If you look at the convergence, so that's the convergence history, the number of iterations, and then here the relative residual reduction. If you look at the current solver, the residual goes down very nicely. I mean, there are big jumps, but it goes down and then it kind of flattens out. If you look at the multigrid, it just goes straight down. So the number of iterations for the multigrid is much, much smaller than for the Krylov method. And if you go to tighter tolerances, so the Met Office is talking about going to 10 to the minus 4, then this is kind of becoming more and more significant. So these are just absolute numbers. So what you see here, I mean, the multigrid is around 2 times faster. The other thing that's interesting about this plot is kind of at around the same time when we implemented the multigrid, Chris Maynard looked at replacing the double precision arithmetic by single precision arithmetic. And what that basically means, I mean, this implementation, I should say, is not really matrix free. I mean, here you still have to store the matrix. So it's basically still a memory-bound implementation. But if you go from double to single precision, you save kind of a factor of 2 because you only have to move half the memory. And that's why you see these big gains kind of here. So there's like, so the hedged curves are the single precision numbers and these are the double precision numbers. And you see this big jump here. So for the multigrid, it's less pronounced, but there's probably still scope to do something here. But I mean, the multigrid is, I mean, significantly faster, and then you gain something from single precision. Okay, so let's look at the other example. So that's hermetic finite elements. So basically, if you have if you have a more complicated domain, or if you kind of want to kind of scale your global grid to very high resolution, you have this pole problem. So you end up with this kind of clustering of grid lines around the pole, and you kind of have to come up with a different grid. So you can't really use this nice structured grid. So the metaphys is moving over to unstructured grids, and then obviously you have to worry about finding a good discretization for this. And then Colin Cotter and others came up with this hermetic discretization, which basically are built. You basically construct function spaces that. And you put your fields into the right function space. You put the velocity into a function space which lives on the edges here, and you put your pressure into a function space which is a DG space and which lives on the cells. And if you do this, you can then basically show that these vector calculus identities are kind of preserved exactly, and then this gives you very nice kind of numerical properties, and it's very similar to kind of secret staggering at low order. So these discretizations are very nice. So what's the problem with these? Well, the problem with these when you want to solve your system in the implicit time stepping is that you end up with a slightly more complicated matrix. So when you look at the system matrix A in this case, I mean, remember we had only ones on the diagonal before. Now you have these mass matrices here. So you have a velocity mass matrix and you have a pressure mass matrix in this case. The pressure mass matrix is kind of block diagonal, so that's not a problem. But the velocity mass matrix is kind of is not diagonal, so that's really, it's a sparse matrix. And if you take this system here, and again you write down the Schur complement decomposition, you end up with the Helmholtz operator, which is not sparse, because the Helmholtz operator looks like this. So you have the pressure mass matrix, then you have again mu squared divided by 4, then you have these derivatives here. So before, this whole thing was just a Laplace operator, but now you have this mu inverse centrage between the two derivatives. And the problem with this is now that although the mu is sparse, the mu inverse isn't. So this whole thing is a dense operator if you do it like that. So that doesn't work. So and the trick here is now, I mean, at least the trick we tried is now to basically just take the system here and basically say, okay, let's just replace this mu by a matrix which is approximately the same, but which doesn't have any kind of off-diagonal couplings. Okay, and then we use this as a preconditioner. So you basically replace this mu by the mu tilde here, and then again you write down the Schur complement, and then you end up with this, and you end up with the Helmholtz operator, which is purely local, because the mu tilde inverse is just diagonal, so you can just do this. So the downside of this is that you now have to kind of really do an iteration over the outer system, because you're kind of solving an inexact system when you do the pressure solve. So that's a bit more complicated. Okay, so just some results. So here we looked at the 3D model system. So that's just linear gravity waves on a 2 + 1 dimensional extruded grid. So you have these equations for velocity, pressure, and buoyancy. It's all linear. And when you write this down, you end up with a system for the pressure and the velocity, which looks exactly like what I've shown on the previous slide. So it has exactly the same structure as the kind of the shallow water system, but I mean, these just have different interpretations now. And then we solved this with this Schur complement preconditioner, and this was implemented in PyOP2 and Firedrake. So, and here are some results. So we did this at kind of two discretization orders. We looked at lowest order elements, and we looked at kind of one order higher elements. So they're called next to lowest order elements because the reviewer of the paper didn't like the term higher order because they're still probably quite low order. But there you go. So it's all relative, yeah. So these are the kind of two discretizations we looked at, and then we compared different solvers. So we always solved this on a full node of Archer. We set the CFI number to 8. Then we compared a geometric multigrid, a single level method, and an AMG method for these two different discretizations. And one thing you can see when you look at the convergence plot is that the multigrid methods again basically go straight down, so they converge really, really quickly. And the single level methods in green, they kind of stagnate at some point and they get kind of much worse for tight tolerances. If you look at total time, so that's this column here, the multigrid methods are about 2 times as fast as the single level method. So that's kind of a factor 2. That's about the same factor that you saw for the endgame solver. It's again a factor 2 that you gain. But the other thing you see is that now the geometric multigrid and the algebraic multigrid are about the same. So that's very different from the first discretization where I was on a structured grid and where I had a very simple discretization. So here, I mean, we worked quite hard to get this working, but the gain is very minimal. Okay, so I mean, it's the same for lowest order and for higher order, you maybe gain like 5 or 10%, so it's maybe not really worth it. And the reason for this is very simple. The reason for this is simply that for the geometric multigrid, for this discretization, we have to store the matrix. There's no way around this. And then you're still matrix bound, memory bound, and you move around the same amount of memory in both cases, so it's not surprising that you kind of get the same result. Okay. The number of iterations is also about the same. Actually, AMG is a bit faster at lowest order. But if you look at the single level method, I mean, this again has requires much more iterations. Okay, so the main lesson here, as I said, was that geometric multigrid is not really faster than AMG at lowest order. So, so you might say, okay, why don't you use matrix free? And we looked into this, and that's kind of shown here. So if I just look at applying the matrix, if I look at lowest order next to lowest order, if I do this in a matrix based way, so that's these black numbers here, then I have an additional kind of cost for assembling the matrix in the first place, so that's quite high. But then applying the matrix is actually much cheaper than applying the matrix in the matrix free way. Okay, so that's about like 4 to 5 times faster, the matrix matrix-based apply. That's a huge difference in both cases. So and why is that? Well, the reason is very simple. The reason is simply that if you look at the numbers, so if you look at both implementations and you count the number of flops and the memory references, if you look at the matrix-free method, you do around 100 times more flops. And that's simply because you have to evaluate, for example, the Jacobian and lots of other things at every quadrature point. So, I mean, even though you get a matrix-free method which runs at kind of a very high percentage of the peak flop rate, so this makes very good use of your CPU, because you do much more flops, it's not faster overall. So in this case, it's actually better to use a matrix explicit method, but then you kind of suffer from the memory bound.
So I think just a comment, I think so
yeah.
Since we got these results, I think we've done some stuff so that number of flops drops quite a lot.
Okay.
But
yeah.
Like the same kind of idea still.
So Lauren said that they did some work in FireDrag to drop the number of flops. So I mean, what was the key optimization?
So we're using better quadrature.
Okay.
And we can do some factorization.
So Lauren said they use better quadrature and they do some factorization, and some factorization is something I will mention on my last slide. So that's basically a trick that you can do to reduce the number of flops on particular elements. Okay, so but I mean, I guess did it drop by 2 orders of magnitude? No.
But like one is, so yeah, you'd have to run the numbers again to like find out if it was worthwhile. But like,
Okay.
it would probably bring you to a tipping point. Maybe.
Yeah. Okay. Okay. So good. So yeah, that was that. Just to briefly mention, there's other approaches. So I mean, I'm not an expert on this. I think Colin has worked on this. There's other approaches for getting around this this dense velocity mass matrix. So one of them is to use hybridization. So basically, what you do is you replace your continuous velocity space by a discontinuous velocity space. So that gives you a block diagonal mass matrix. And then you enforce the continuity with Lagrange multipliers. So you basically add additional variables to your system, which guarantee that kind of these jumps between the elements are actually 0 in the end. And then you write down a bigger system, which has, in addition to the velocity and the pressure, it has this Lagrange multiplier here. You do a Schur complement reduction. You end up with a system for the Lagrange multiplier. And you solve this, and then you kind of reconstruct the velocity and the pressure. And this, you can show that this kind of works. So it's a bit, well, the tricky bit is that these Lagrange multipliers live on the element edges. So you can't, I mean, you have to think carefully how you construct your multigrid, but there's these people who implemented this hybridized multigrid and showed that it works. So, I mean, that's kind of an alternative approach. There's probably others, but I don't want to go into this here. Okay, so, right, since we mentioned some factorization, coming to the last few slides. So the last thing I want to look at is higher order discontinuous Galerkin. So in this case you have, okay, I wrote down we use a structured grid. That's not really necessary. What you need is you need kind of elements that have a tensor product structure. So the grid doesn't necessarily have to be completely structured. You can also do this on, in principle, you can do this on triangles, but it's a bit more tricky. You have to use Bernstein polynomials or something like that. Okay, so, and the nice thing about this is that this allows you to go to higher order very, very easily. And you can then play these tricks with some factorization, which really kind of pay off if you go to a higher order. Okay, so how does this work? So as I said before, so one issue with all non-trivial low-order discretizations is that they're either bandwidth limited, if they're matrix-based, or the number of flops is simply excessive if you implement them in the matrix-free way. So in this higher order methods, they kind of offer a way around this. So basically what you do here is you basically say that your solution, so the velocity and the pressure, basically all variables live in these discontinuous function spaces. And on each kind of element of your grid, the solution is represented by a high order polynomials. And you allow jumps between the cells, so it doesn't have to be continuous. And then, I mean, you obviously, you somehow have to make sure that these jumps vanish as you increase the resolution, but there's kind of techniques for doing this. Basically what you do is you introduce penalty terms that kind of pull these jumps to kind of 0 as you increase the resolution. So basically, yeah, you do this, you approximate the solution by this high order polynomial in each cell, and the degree of this polynomial is p from now on. So these discretizations have some very nice properties, so they're inherently conservative. If you have a solution which is sufficiently smooth, they also kind of converge with kind of the grid spacing to some power p plus some small number. So p is the polynomial degree. So that means that if you have a smooth solution, the total number of unknowns that you need to kind of represent this is much smaller if you want to kind of have a fixed error. So that's very nice. The other thing that's nice about them is that if you implement them on a parallel machine, because the data is kind of discontinuous, it's very kind of contiguous in memory. Because you store all the data in one cell, you can store that in one contiguous block of memory. So getting this out of memory is kind of very, very efficient, and you don't get any kind of overhead from indirections that you get on for a conforming method on an arbitrary grid. So yeah, so there's some really nice properties here. They have been applied to fluid flow. So this is a list of some papers which basically use these methods. It's obviously incomplete. I just mentioned a few papers I looked at recently. So one thing people have done a lot, they have used DG with explicit time stepping methods. And that's kind of that's kind of a solved problem. It's known how this is how to do this. Problem with this is a bit that the CFI condition kind of, obviously restricts your time step size, and the restriction is typically something like this. So the CFA number has to be smaller than 1 times twice the polynomial degree plus 1. So that's from this paper here. That's for a particular problem, so that might not hold for any problem. So if you use a higher degree, you have to kind of use a tighter time step, and that's kind of a problem. So then people obviously have tried to get around this and use, because remember what restricts your time step is the kind of very fast waves that you don't have in a semi-implicit method. People have started looking at implicit methods. So there is, for example, this paper by some people from Heidelberg. So they applied implicit methods to the incompressible Navier-Stokes equations, and they used the projection methods. Cohen's projection method, and they end up with solving a Poisson equation, and they have a high order DG solver for this, and they also have a matrix-free implementation of this high order DG solver. So this runs at very high speed if you are at high order. So people have applied this, so the same group applied this to porous media flow, so they just used an implicit splitting method. So again, you have incompressible Darcy flow, and then you have, that's basically your Darcy flow here. It's incompressible, so when you take the divergence of this, you again end up with a Poisson equation for the pressure, and you again solve this with the DG method. So people have applied this to the shallow water equations. So this paper from 2009, they've done this, they've written down a semi-implicit equation, but then they end up solving the mixed system, so they haven't got a good preconditioner. There is kind of some ideas how to apply this to compressible Navier-Stokes. So that's another paper by the same group. But constructing a good Helmholtz preconditioner is apparently still an open problem. That's what Frank Giraldo told me. So it's not so obvious how to do this. Because in DG, even though the mass matrix is kind of diagonal, you get flux terms which again cover the cells, so you're kind of back to the same problem as before. Okay, so just few comments on some factorization. So this is some recent work we did. So we looked basically at this advection diffusion equation. How you then actually get this DG discretization of this equation from the time stepping is kind of a different question, but let's just assume we have this. So let's assume we discretize this in DG and we want to solve this. And to do this, basically, again, you have to apply the operator, and you need a good preconditioner. And the good news is that if you do this in a matrix-free way and you use some factorization for doing this, you basically reduce your computational complexity and you also minimize your storage requirements. Okay? And the way this works is basically, I don't want to go into the details of some factorizations, but if you just look at this, if you look at 3 different methods, so the first one is matrix explicit. If you look at the number of flops, the number of flops is the degree to the power of 2d, where d is the dimension. If you do this in a matrix-free way, the number of flops doesn't decrease, but the number of memory references decreases, so that's obviously nice because you don't have to store the matrix. But remember that you have to do lots of flops, so this method isn't necessarily faster. So now the trick is to use the sum factorization, and what the sum factorization basically does, it kind of takes the matrix A, and it assumes that the matrix A is a tensor product of kind of matrices in different directions, and then it applies them step by step. And what you can show is that you can show that the number of flops in this case is much, much smaller. The number of flops is just the dimension times p to the power of d plus 1. And that is, if the p is very large, this is a huge kind of improvement. Okay, so the number of flops really goes down, and the arithmetic intensity is kind of still large in these methods. Okay, so Steffen Müttinger in Heidelberg actually implemented a really, really good version of this operator. So this runs really, really fast. It runs at around 30% of peak using these techniques. What was still a problem is kind of constructing a preconditioner, because to construct a preconditioner, you kind of need to kind of assemble the matrix typically, and we did some work on this. So basically what we did here is we used this kind of hybrid preconditioner where you use a DG smoother on the coarsest level, then you refine to the lowest order subspace, and then use IMG on the larger level, and then you go back. So that's kind of a hybrid multigrid algorithm where you use a DG smoother here, and then you use AMG on the coarser levels where you have a low order discretization. And then the challenging bit, the expensive bit, is applying this DG smoother. So the smoother looks like this. So basically what you do in each iteration, you apply the matrix. So we know how to do this. We can do this really, really fast with the sum factorization. But then you have to divide by these blocks here. Okay, so and these blocks here, these are the block diagonals of your matrix. And typically what you do is you assemble them in each cell. And then you do some factorization, LU or for Cholesky or whatever, and then you divide by this. But the problem with this is that you still have to assemble these small blocks, and you also have to kind of store them, and you have to do the LU solve. So that makes the problem memory bound again. So all the gains you got from this kind of from this fast sum factorization operator is kind of lost when you do this. So the trick here that we kind of tried out was basically, instead of inverting these blocks exactly, we basically just invert them with a small number of iterations. And we actually don't invert them exactly, we just invert them to some tolerance epsilon. And then, this is a preconditioner, so you probably get away with this. And then we use this, and then, if you do the iterative inversion of the blocks, you obviously only have to be able to apply them, and we can do that in a very fast way because we have some factorization for them. So that basically gives you a solver that's entirely kind of matrix free, and it's high order, and it's still like a fairly advanced discretization. So here are just some results. So what I'm just showing here is that's an inhomogeneous diffusion problem solved here. So this is the cost per unknown as the polynomial degree increases, and what you see is the red curve, that's the matrix-based method, and what you see is that for low degrees, for degree 2, it's still competitive, but if you go to higher degrees, it just goes through the roof. And then if you look at the blue curves, so the blue curves are basically the totally matrix-free methods, and I inverted these kind of blocks to different tolerances, and if I choose a very loose tolerance of around 10 to the minus 2, then I'm actually doing really, really well. Even at lowest order, I'm at about the same speed as the matrix-based method. And then as I go to order 3, for example, I'm much, much faster already. So what's the green curve? So the green curve is also not bad. The green curve is basically the curve where I apply the matrix in a matrix-free way, but I invert the blocks in a matrix-based way. Okay. So that might be the fastest method, but the problem with this is still that you have much, much larger storage requirements, which kind of limits the problems that you can solve. Okay, so I'm almost done. Just to say, we also applied this to more complicated problems. This is the SPA 10 benchmark, where you have these jumping coefficients. So there the matrix free isn't doing quite as well. This is a much harder problem. But at order 2, it's already at the same speed, and at order 3, you can't use the matrix-based method simply because you run out of memory in this case. Whether you want to solve this problem with these jumping coefficients to degree 3 is a different question. Okay. Right, so I think I stop here. Just a few comments and then have a few questions, so maybe they help with the homework. Basically, one of the lessons that we learned is that matrix-free pays off for very simple discretizations, and if you have higher order DG, and high means second or third degree, so it doesn't mean ridiculously high degree. So for low order discretizations, it's usually very hard to beat AMG unless you have a very simple discretization on a very simple grid. And finite element solvers are just challenging due to these non-diagonal mass matrices, so any alternative approaches are obviously very interesting. The other thing we learned is that you can, if you have a problem that's kind of well behaved, you can go from double to single position. You have to be a bit careful. If you do this, you obviously can't solve to very tight tolerances. Even if you just go down to 10 to the minus 6, you might lose orthogonality in your Coulomb subspace, so you might have to restart, and the number of iterations goes up. The interesting thing, I think, is that this higher order DG method is very attractive for modern architectures. Okay, so here's just a few questions, topics for discussion. So one thing is obviously if we implement these solvers, how do we do this to exploit modern hardware? One challenge is that you really need to vectorize in the innermost loops, so that's one of the reasons it's challenging, and Lawrence will say more about this. The other question is obviously what happens in other time-stepping methods? Can we use the same solver techniques in other methods? What can we carry over? And then also, if you look at higher order discretizations, so for low order discretizations, I said usually AMG is a really good approach. Just take a library, take your AMG solver, but is there maybe something for higher order discretizations? Do we need libraries for that exploit this? And is there maybe other ways than going higher order? Is there any other tricks? And I think I stop here. Okay, thank you.